Okay, so with this lecture and the following sequence of short lectures I'm going to host on YouTube, we will be discussing limit theorems. So to begin, let's start with this definition. So a sequence X of reals is bounded if there's some positive real number, say m, such that an absolute value n serves as an upper bound on that sequence for each n, right? So in other words, what this means is that if we look at the real number line and we have some sequence, and maybe like 0 is right here, right? And our sequence can do all kinds of things, right? But what it means to be bounded is that it's somehow contained in some block, not an interval, but just like some subset of R's, right? So that's the basic definition of being bounded. And so now we're going to prove our first theorem about convergent sequences and how they're related to bounded sequences. So this is 3.2 theorem. And this theorem states that a convergent sequence is bounded. So any convergent sequence that we've encountered must necessarily be bounded by this theorem. Okay. So what does this look like? What does the proof look like? Well, we just need to get an absolute value that the sequence is bounded above by some positive real. And the only information that we're given is that it's convergent, okay? So there's a clever trick that we can do. Not a trick, but just a clever idea. We can say, take epsilon equal to 1, so that's some positive epsilon, right? And since the sequence in question is convergent, well, actually, let me say what the sequence is first, just so we can use it notationally. So maybe let X be a convergent sequence. Let's go ahead and define what the limit is. With limits xn equal to x. And now I'm going to choose epsilon equal to 1, and you'll see why in a moment. And choose epsilon equal to 1. Now, since this is a convergent sequence, we know that there is some cutoff in the indices where after that cutoff, xn is within distance epsilon to x. So I'm just going to state that now. So then there exists some index k such that if n is greater than or equal to k, then xn minus x is at most 1. Okay, so we just know that that's going to be the case. Next, observe So we're going to try to get an estimate on x of n. Well, what we can do is do this add and subtract thing that we often do, right? So we can say right, we just added 0. And then we can group these in a way that we can make use of this observation. So I'm going to say the minus x is going with the sequence xn. That. Then we can use the triangle inequality. Like that. And then we know that this piece of this sum is bounded above by 1 whenever n is greater than k, or greater than or equal to k. So this is at most 1 plus the absolute value of x. And again, whenever n is greater than or equal to k. Okay. Now, this is good in a sense, right? Because we've shown that the magnitude of the sequence whenever n is greater than or equal to k is bounded. That's just a number and that's a number, right? So this is a bound on there's infinitely many pieces from the sequence after n passes k. So at this point, you should realize that the sequence in general should be bounded. Why? Because after k, all the x's are bounded above by this, and then below k, there's just like some finite collection of numbers to choose a supremum from. So then we can say, so then we choose m to be equal to the supremum of the absolute value of x1, the absolute value of x2, dot, 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 the absolute value of x k minus 1, and then this. 1 plus the absolute value of the limit. As I was just saying, there's a finite number of terms before we reach k, so we just take the supremum of all of these together with this bound here. We have another bound, because now everything in the sequence is no more than that. And observe that in magnitude, the sequence is bounded above by m for all n that are natural numbers. Okay, so this completes the first proof in my series of limit theorems. So I'm going to stop the video there, and then I'll record the next one.